It's a problem so vast, so incredibly complex, that even with computing power beyond our wildest dreams, a supercomputer testing A*billion roots per second, it would take over 10 to the power of 200 years just to solve it. That's the staggering reality of estimating over 10 to the power of 220 possible North American road routes. Yet, in a mere 4 seconds, Google Maps delivers the optimal path. This isn't magic, it's a testament to a scientific journey, beginning with a man whose groundbreaking work was initially met with sheer disbelief. Imagine the sheer audacity. In 1956, a visionary named Edgar Dijkstra, on a quest to simply demonstrate the raw power of the ARMAC computer, unwittingly laid the very foundation for modern navigation. His concepts were so revolutionary, so far ahead of their time, that on his own marriage license, his profession was even hilariously mislabeled a theoretical physicist. But his vision, fueled by an undeniable genius, persisted. By 1959, he published his shortest path algorithm in the German journal Numerische Mathematik, a breakthrough that, even today, underpins every single GPS system you use. It's the silent hero making sense of an otherwise utterly incomprehensible spaghetti web of roads. Yet, for all its genius, Dijkstra's algorithm, in its pure form, faces a staggering challenge. For a single route, say from Newark Airport to the Central Park Zoo, it processes over 65,000 nodes in just about a tenth of a second, sometimes even throwing out what seem like totally illogical turns, all in its relentless pursuit of the absolute shortest path. But scale that to the entire North American network, and a finely tuned Dijkstra still needs around 7 seconds, exploring most of its 64 million nodes. 7 seconds. For millions of simultaneous requests, that's simply too slow. We need milliseconds. And here's where the next flash of brilliance arrives, a star. This isn't just an improvement, it's drastic evolution. A* slashes the search space by implementing a clever heuristic. It prioritizes nodes closer to the target using straight-line distance, immediately cutting down exploration to roughly 7,000 nodes. That's a jaw-dropping 10 times improvement, though, and here's the kicker. Optimizing for travel time can actually triple A*'s node exploration compared to Dijkstra's mere 10% increase on larger graphs. It's a subtle complexity that reveals the constant tightrope walk of optimization. But the pursuit of breathtaking efficiency never stops. Next up, bidirectional Dijkstra. This ingenious strategy tackles the problem from both ends simultaneously, with two searches meeting somewhere in the middle. Imagine two explorers converging. This overlap, around the midpoint, R2, covers half the area of a single search, achieving close to A*3 times improvement. A route like Carnegie Hall to Wall Street, it shrinks from Dijkstra's over 7,200 nodes to a mere 2,600. Simply incredible. However, the truly mind-bending leap, the one that unlocks near-instantaneous results, came with pre-processing road hierarchies. Initially, this was a manual, painstaking endeavor. Surveyors literally categorized roads by hand: express highways, major local roads, narrow residential streets. But since the 1990s, GPS systems have been leveraging these pre-computed road classes, running bidirectional Dijkstra within these predefined candidate areas. This foundational concept then exploded into automatic graph pre-processing, ranking nodes not just by distance, but by sheer hierarchical importance. Think about it, critical nodes like a bridge that splits two towns, or the majestic Mississippi River that acts as a natural bottleneck, are identified using advanced techniques like nested dissection. For the entire North American network, just the top 102 most critical nodes can split the entire graph in half. Subsequent cuts then naturally follow geographical features like rivers and mountain ranges. And then, at the lower ranks, absolutely smart, algorithms build shortcuts making sure no shortest path is ever missed, all while drastically limiting the search space for your real-time queries. It's a symphony of computational genius. So, the next time that instantaneous, effortless journey flashes on your screen, remember this. What you see is the culmination of decades of profound algorithmic ingenuity. It's science transforming an impossible calculation into an everyday convenience so seamlessly, you barely even notice the sheer wonder of it all.